Hello. In this video, we're going to learn how to answer questions about normal distributions that are not the standard normal distribution. For example, take a look at this situation. Scores on a test are normally distributed. The mean is 80, the standard deviation is 5.4. What is the probability that a random person scores above 83? Now, this is a normal distribution, but it's not the standard normal distribution because the mean is not 0 and the standard deviation is not 1. So how do we answer this kind of question? Well, we can draw a picture of a bell-shaped curve. All normal distributions have a bell-shaped curve. We know the mean is in the center of the bell shape, so we can put 80 in the center of the bell. And we're asking about the probability that this person scores above 83. So we can mark down 83 and we can shade that area. Now the question is, how do we find that area? The chart that we were using in the previous section to find areas under a normal curve was only valid for the standard normal distribution. And this one, like I've said, is not the standard normal. Well, it turns out that any normal distribution can be transformed into the standard normal using z-scores. So what we can do is we can take our normal distribution, which is centered at 80 and has an area shaded to the right of 83, and we can convert those numbers into z-scores. And what we will have at that point is a standard normal distribution with the same amount of area shaded to the right of whatever the z-score is that's corresponding to 83. So you might remember our z-score formula from chapter 2, value, or maybe it was chapter 3, value minus the mean divided by the standard deviation. Now, when we learned about z-scores in chapter 3, I told you that the mean of a data set will always convert to 0. If the value and the mean are the same number, you're going to get 0 divided by the standard deviation, and 0 divided by anything is 0. So that's why I know the mean, 80, automatically converts to 0. But what about 83? Well, take that value, 83, subtract the mean, 80. That gives you 3, divided by 5.4, and you get 0.56 as your z-score. So the amount of area that was under the curve to the right of 83 in the original normal distribution is the exact same amount of area that's shaded to the right of 0.56 in a standard normal distribution. So now we're just back to doing what we learned how to do in the previous section, which is finding the area to the right of some z-score in a standard normal distribution. So you might remember what we have to do. We have to look up this number 0.56 in the standard normal distribution chart. So let's go to the row for 0.5 in the column 6, and that gives us the number 0.7123. Now that's the area to the left of the z-score, so that's the unshaded area here. If we want the shaded part on the right, well, we learned last time what we have to do. We just take that number away from 1. 1 is the total area under the curve, subtract the unshaded portion, and what you're left with is the shaded piece, and that would be 0.2877. So anytime that you have a normal distribution that is not the standard normal distribution, all you have to do is convert everything into z-scores, and at that point, you're back to a standard normal distribution, and you can do what we learned in the previous section. That's true whether the area you shaded is to the right of a z-score, to the left of a z-score, or in between two z-scores. Now there's another kind of question that we want to look at in this section, and that's what we call a cutoff question. So for example, we might have a situation like this, where a college gives an entrance exam to all of its applicants. The scores are normally distributed. The mean is 72.3 and the standard deviation is 5.2. Now, maybe the bottom 10% are not admitted into the college. Well, if that's true, you're going to want to know what score do you need to beat in order to get in. Okay, well, here's what's going on. We have a normal distribution. So let's draw the bell-shaped curve. The mean is 72.3, so let's put that in the middle. Now, there's going to be some score on the test that separates the bottom 10% from the other 90%. So I've shaded that area to the left of what I've called X because that would represent the lowest scores. And I've labeled that shaded area 10% because whoever scores in that region, those 10% are not going to get into the college. Now, I'm looking for this value of x, okay, the test score that's going to separate those 10% who do not get in from the other 90% who do get in. Now, I'm not going to be able to find that value of x directly. What I will be able to find is the z-score for that value of x. Okay, and the reason why is I can go to a standard normal distribution chart and I can figure out the z-score that has 10% of the area to its left, which in decimal form is 0.1000. So let's go to our standard normal chart and let's see if we can find the number 0.1000. Okay, now that number that we're looking for is on the left side of the chart, so it's going to be a negative z-score. And let's see, we're looking for the number basically 1,000 if you ignore the decimal point. And it's not in the chart, but it's in between these two, 0.1003 and 0.0985. The number 0.1000 is closer to the 1003, so we'll go with that z-score, which is negative 1.28. So our z-score is negative 1.28. Now the question is, what is the value of x that would produce that z-score? Well, remember the z-score formula. Z is equal to the value x minus the mean divided by the standard deviation. If I just do the algebra to solve this equation for x, it would look like this. X is equal to the z-score times the standard deviation plus the mean. So if I plug in the negative 1.28 z-score times the standard deviation 5.2 and add to that the mean of 72.3, I find out that the x value is 65.6. That's the value that separates the bottom 10% from the other 90%. Now maybe the top 5% will receive a scholarship to this college. So you might also want to know what score do you need to beat to receive the scholarship. Well, this time we're looking for the value of x that will separate the top 5%. So we're going to shade that area to the right of our value of x on the right side of the distribution because that represents the highest scores or the top scores. We're going to call that area 5%. Okay, the 5% who score in that area are going to receive the scholarship. The other 95% will not. Well, 95%, that's the area to the left of the value. So that's what we're really going to have to work with here. In decimal form, that's 0.9500. Now, like I said in the previous question, we're not going to be able to find that value of x directly. We're going to have to find the z-score first and then go back and figure out the value of x. So what, in a standard normal distribution, what z-score has an area of 0.9500 to its left? Well, let's check the chart. On the positive side, we're going to, let's see, we're going to have 0.9495 and 0.9505. So the number we're looking for, 9500, is halfway in between those two values. Now remember from the previous section, whenever the number we're looking for is exactly halfway between the two values, we have to average the z-scores, which in this case would be 1.64 and 1.65. Okay, there you can see the row and the columns, 1.64 and 1.65. So I average those z-scores, add them up, divide by 2. That gives me 1.645, which when I round to 2 decimal places is 1.65. Now to get the value of x, I just use the formula that I showed you in the previous part, multiplying that z-score by the standard deviation, adding the mean, and that gives us, in this case, 80.9. So 80.9 would be the value of x that separates the top 5% who get the scholarship from the other 95% who do not. Okay, so that's how we work with normal distributions that are not the standard normal distribution. Not too big of a deal. Okay, if we're looking for probabilities, just convert the values of x into z-scores, and then essentially you've got a standard normal distribution. You can go back and do what we learned how to do in the previous section. In these cutoff questions, you'll start by finding the z-score, and then you'll just convert that back into an x value. So it's really just one additional step above and beyond what we learned how to do in the previous section when we learned how to work with standard normal distributions. There's just a conversion related to z-scores. That's the only additional step you have to take when the distribution is normal, but not the standard normal. Okay, that's all for this video. I'll see you in the next one.